clock routing or doing some engineering change order or following the DRC rules for maintaining the minimum width and space between the nets, cells, and macros. Okay. So core utilization is basically calculated by macros area plus standard cell area. So macros area, if you are designing this macros, you will have the macros area. And standard cell area, we get this from synthesis. Okay. And next is divided by total core area. Total core area is nothing but length into as it is a rectangle. Okay. Consider the core utilization is okay. Macros area is 5 and standard cell area is 20. Okay. Divided by total core area. We get the total core area by 9 cross 5, that is 9 5 is 45. So what will be our core utilization? 25 divided by 45. 5 5 is 5 9. So what we will get? That is nothing but we are getting a core utilization of 0.5%. That is 55%. That is, we are taking a core utilization of 55%. And remaining, whatever 45% is there, we are using it for signals and clock routing. Hope this slide is clear. How we are estimating the aspect ratio and how we are calculating the core utilization. Ganesh, Tarak, Bhuvaneshwari, is everyone with me? Understanding how we are going to decide the core area? Anyhow, we know the die area. Core area plus IO offset area will give the die area. Yeah, thank you, Sadiq, Tarak. Sir, how we decide the thickness? Thickness will come from the boundary. Okay. We are going to decide the area of the chip. Okay. Based on the metal layer thickness, the thickness of the chip comes out. If you are taking 9 metal layer, if you are taking 8 metal layer, if you are taking 4 metal layer, based on the number of metal layers we are using, we will get the thickness of the chip. If you are using 4 metal layer, example consider you will get 4 mm. If you are using 5 metal layer, 5 mm. Consider example. Okay. This is how the thickness will be given by fountain. Based on the number of metal layers we are going to use. Clear? Durga. Durga, did I answer your question? Sir, in the core utilization, why don't we add a routing area? So, floor plan is a stage where we are deciding the core area and die area. Okay. We are here to estimate how much area we want to use for our chip. Bhuvaneshwari, please listen. Okay. So, in floor plan stage, we are supposed to do only the area estimation, how much we need to use for our chip design. As we know the macros area, as we know standard cell area, okay, we have that areas. Okay, so we are using these two areas to get some sum here as per the formula. Okay, and next we are getting the total area. How we are going to get the total area? By checking the core utilization. If we are using 60% of core utilization for placing the standard cells and macros. Okay, remaining 40% we have to use for clock tree synthesis and routing. As the routing or clock tree we are not doing, we are estimating it. If the routing and clock nets are more than 40%, okay, we may face some issues. What are those issues? We'll learn in the next slides. We will get congestion, routing congestion, we will get minimum space violations, we will get shorts, we will get break of nets, we will get antenna violations, and all these violations comes in the chip. If the routing and clock tree synthesis is more than 40% utilization. So what we will do? We will increase the chip size. But we are not supposed to do that. As per the customer, they will give you the dimensions or core size or die size, this much area only you have to decide, and this much area only you have to design the chip. As we see on our mobile phone boards or small electronic gadgets, the chips are very small size, but there is a lot of logic sitting on them. Why? Because we need to accumulate more amount of logic, more functionalities we need to add. Earlier, in a smartphone, we used to have each and every sensor, each and every chip. But nowadays, they are clubbed together to form a single chip. Sensor module, wireless module, SoC, 2G, not this, GSM, GPS. These all chips sit together on a board. If all these chips sit together on the board, making that connectivity, the board size is increasing. My mobile phone size also will increase to your monitor size. To avoid this, whatever the customer protocol or he has given some area, okay, 9x5 dimensions you have to use for your chip design. We have to decide that and we have to proceed further. And if we are getting some violations, if chip doesn't work, we need to talk to customer. If the customer is reasonable, if he has plus or minus values, he will give the flexibility. If they don't have the flexibility, we have to fix that and we have to do in that area only. Got it, Bhuvaneshwari? Yes, sir. Thank you. So any questions or any doubts in this slide, we'll proceed further. How good the floor plan is, that good the chip is. See, if we are constructing a house in 200 square yards, once we build the basement and start building the pillars and slab, okay, can we do any modifications? We can do, but that will cause loss of destruction. Without doing that loss of destruction, we have to reconstruct it. Is it possible? We can do minor changes, but we cannot do the complete changes. This is how we decide the basement step of physical design. Floor plan is very important to decide the basement step of physical design. Yes. Thank you, Ishwar. Clear so far, everyone? So, possible to design in circular shape? Durga, yes, it is possible, but most of the times, okay, they will prefer two kinds of shapes: linear shape and rectilinear shape. Linear shape means it's like square or rectangle. Okay, the rectilinear shape means it will be like this. Most of the times, customers prefer linear shape. Those are like square and rectangle. And if the board area is little bit difficult and it has some other constraints, okay, yeah, triangle is also possible, but they prefer linear and rectilinear. Most of the tools support these two kinds of shapes, either linear or rectilinear. Okay. Arshita, is that fine? Okay, Durga. I'm moving to next slide. If you have any questions, right. Thank you all. Next is port placement. So how we are going to decide the port placement of pin placement? Pins can be spread automatically by IC compiler or Innova tool around the membrane. The exact side, location, layer size, and the pin can be set by the designer. So what we will do is we have a chip. This is my macro. These all were my standard cells. Okay. This is my core. This is my die. So most of the macros, they will be having pins. Okay. So these pins for this macro. Okay. So tell me which side of the macro there are more number of pins. That is more density pins. So we will place towards the corner of the core area. So these pins can get directly connected to the IO port. This is why the reason we will place the pins the more pin side we will place towards the IO ring side and the less pins we will place towards the core side. Based on the pins, number of pins or the density of the pins for each and every standard cell or the macro or when we click on this in the tool that will give the connectivities. So based on the connectivities, we have to move the direction of the pins or we need to align the modes. Clear? Blackbucks, can you help Ms. Bhargavi to join the session? Okay, right. How we are going to do the ports placements based on the pins, density of the pins, side of the pins, and layers of the pins. Clear? Macros and macro placement. As we have decided, there are two types. And what are macros? Macros are special designed cells. That means I am designing a SOC. In that SOC, I have a wireless chip. What all are the wireless properties we have in our mobile phone? We have wireless connectivities like NFC, near field communication, Wi-Fi, Bluetooth, okay, hotspot. Hotspot also will use the protocol of Wi-Fi and Bluetooth. So these are the main three wireless communications: NFC, Bluetooth, Wi-Fi. So using these three modules, I'm going to build a macro. Some company has built this macro and they have given it in the form of a macro. So directly I can use this macro in my design. This is a specially designed cell. Macros may be memories, analog blocks, or any kind of design sets. Proper placement of macros has a great impact on the quality and performance of ASIC design. So when we place this macro, okay, so as per the tool, when we click on this macro will give you the fly lines. Fly lines is nothing but the connectivity to the outer core of the chip and inside logic to the chip. Based on that fly lines, we will be arranging the orientation of the macro. That is what the macro placement will impact the good quality performance of ASIC design. Macro placement can be manual or automatic. Even automatically the tool places also. Okay, we have the flexibility to move. Generally, macro placement is preferable manually. Next is types of macros. Hard macro, soft macro. Hard macro, the circuit is fixed. We cannot see the functionality information about macro. Only we know the timing information. Next is soft macro. The circuit is not fixed. And we see the functionality and type of the gates present in it. Also, we know the timing information. So there are two types of macros. One is hard macro and the other one is soft macro. Hard macros are the chips or the circuits or the already designed logics where we cannot see the functionality of the macro. But we have the timing information. They will give you the timing file. Soft macro. Soft macro, we know what is the logic inside that macro, what functionality it is doing, okay, and we have the timing information of the soft macro. Understood? What is macro? And what are the types of macros? What is the impact of macros placement? Yeah, Tarak. Sir, Verilog or VHDL, a port is used just one pin, sir. Yes. So like that, we define some n number of pins, n number of ports in Verilog. Okay. Considering all that pins and ports, we will be building a IC. Yes. The nets, wires, all are signal nets, clock nets. How far can we change functionality of a soft macro? See, soft macro, Bhuneshwari, there are two concepts. I am ABC company, okay, and there is some XYZ company. I bought the soft macro from XYZ company, okay. I want to use it in my company. So what they will do? They will give you the soft macro. They will sell you that macro. We cannot change the logic of the soft macro, but we know what is the logic of that macro. Just we can change the connectivities. See, there are soft macros. Example, as I have told you, I am using a wireless chipset, which has Bluetooth, NFC, and next one is Wi-Fi. Samsung company has bought this chip from Texas Instruments or Qualcomm. They have assembled it on the Samsung mobile phone board. Okay, based on the price constraint, based on the time to market, they have only integrated Bluetooth and Wi-Fi. They have left out the feature of NFC. If they want to enable NFC, they can enable in the software updates in the future. If they don't want to enable, they can maintain the same price. They don't have the control or changing the logic in the functionality. They have the control about understanding the logic of a functionality and how to reuse it in our design. Clear, Bhuvneshwari? Sir, without knowing functionality in the hard macro, how can we use it efficiently? Good question, Bhuvneshwari. So, if you go to embedded systems and IoT, okay, I want to interface temperature sensor LM35, okay, to my Arduino IDE. What we will do? We'll just directly connect the pin out of LM35 VCC ground and analog pin out to my Arduino board, and we'll run the code and we'll get the analog values, temperatures. That's it. Similarly, hard macro, they will give you the data sheet, but we don't know the functionality inside what they have written. It is their proprietary. Okay, macros are nothing but they are IPs, intellectual properties. They may get their patents also. Okay, they don't want to show the functionality. Soft macros basically they will do inbuilt in-house. Hard macros they will get it from other companies. If they have good communication with both the companies, they can get it as a soft macro also. It is how their agreement is. But hard macro, we have pinout diagram and we have the data sheet and how to connect to our logic and how to check with our logic, how we want to use that hard macro, you can get that information. But not the detailed explanation of functionality of hard macro. Just they will give you the pinout and how you want to interface, you can interface it in your floor plan and placement. Clear, Bhuvneshwari? Not exactly. Hard macros is like sensor we buy. Not exactly, but as an example. Okay. So some companies they will design Bluetooth with 5 gigahertz of frequency, and somebody design at 2.5 gigahertz of frequency, but they have the variable frequency also. But when they are giving to us as a hard macro, they will adjust some frequency and they will fix and give it to us. But we cannot change it to 2.5 to 5 gigahertz. But I need a variable of 2 to 4 gigahertz or 2 to 4 megahertz. Can I change in the hard macro? No, I can change it in the soft macro. Clear, Bhuvneshwari? Yes, sir. So there is a question from Tarak. What are macros placed at the boundary? So Tarak, I am explaining based on the pin density and based on the communication of the macro to the outside boundary pins and inside logic of standard cells. We are going to place the macros either on the boundary side or in the middle of the chip. It's all our wish. So as the macro placement is preferable manual placement. We are not going to make it as automatic placement. If you are making automatic placement also, if you are the owner of your chip or if you want to request the manager to enable for editing, then you can move it manually. Clear? Correct. Yeah, fine. Janavi. Rohit, circuit is not fixed. Then we can change the functionality of soft macros. If the company, see, soft macro is nothing but we are getting it from some company, then we need to ask the other company person, can we change the logic? Or can you give us modified functionality what we require? If it is in our own company, we need to request our manager. We need these kind of specifications to be changed or changes in the functionality of this macro. Can we get it changed? If yes, they will give you the changes. If not possible, then you need to adjust and do it for that specification. Rohit, is that okay? Okay, sit down. You want me to sit down? Janavi, we can't see the functionality, but we can know the functionality of our use, right, sir? So Janavi, as I am telling you, add macro. Okay. So they will give you the pin diagram, data sheet. So you have VCC, ground, and output data, and input pin. Those pins, if you are connecting, it's well and good. If they don't give you data sheet, if you have directly the hard macro to connect it, you don't know, then it is very difficult. We don't require the functionality for hard macro. If we want to use it as a soft macro, we need to ask them to customize our logic and functionality, understand. Clear? Janavi? Yeah. Basic constraints. Alignment of macros by edges. Grouping macros in a way that for the standard cell, rectangular area should be left as much as possible. Alignment of macros with core boundary. So as we told, when we click on the macro, when we click on this macro, it will give you some fly lines. Based on the communication to this macro with other logic. If they are communicating more to the logics or standard cells in this side, we need to place the macro towards this side. If they are communicating to the boundaries, okay, we need to place the macro to the corners of the boundaries. Clear? Goal of the macros placement for better routability. If we have the macro here, we have to route easily the nets to the standard cells. Better routability. Next is timing. The length of the nets, the length of the clock nets, everything should be timing reasonable. Reduced wire lengths. So my macro is here, my standard cell is here. Okay. But the pin communicating to this macro is sitting here to this standard cell pin. So it cannot route in this way. So it has to route in this way. So this is long net. So we should try to reduce the length of the net. Clear? Next. More area for standard cells in core region. So as much as possible, we need to use less number of macros, and we need to have our own logic in our core area. That is most preferable. Clear so far, everyone? Yes, sir. Tarak. Thank you. We'll proceed further. Any questions? Ishwar Sai Royal. You are the owner of Royal Enfield. Okay. Continue. Next slide. Macro placement guidelines. Okay. Macro should be placed at the periphery in the block. Avoid placement of macros or stacks near the ports in order to avoid congestion in later stages of physical design. Okay. So if we place the macros in the middle of core area, okay, to route the signal nets, from one end to the other end of logic standard cells, that will give you the congestion. So the first diagram is not possible. This kind of placement of macros is not allowed. We need to place macros in corners of the core area for better sitting of standard cells and better routing of standard cells. Clear? This is one of the guidelines for placement of macros. As I have told you, placement of the macros are based on the fly lines showing the connectivity between macro to macro and macro to ports and macro to another logics. So we can minimize the interconnect length between IO port, macro, and other cells. So when we click on this macro, so there is a lot of communication between these two macros. So if you place this macro here and if you place this macro here, if standard cells are sitting here, okay, so to route all these nets is not possible. So what we need to do, we need to place this macro in this orientation to reduce the routing congestion. If the macros are talking to most of the side of IO pins, okay, these are the fly lines. So we will make the macro to sit near to the core IO pins. It depends upon your area, Hema, and how many macros you want to use. Hema, did you get it? It depends upon your design specifications, how many macros you want to use, and how much big is your chip area. So this is the second guidelines of macro space. Clear so far, everyone? How can we decide how many macros to be placed on a chipset? So already we know the logic, already we know the specification, already we know the design, what we are going to design. If we are going to design a SoC for a mobile processor, okay, the typical specifications are CPU, GPU, RAM, wireless connectivities, okay, ROM. Okay, as I have told you, most of the times we get these three as macros. I want to use 4 GB RAM and wireless connectivity of Bluetooth Wi-Fi and ROM of 64 GB. Already they are predefined hardware software macros. So next is I need to design CPU and GPU. So how many macros you need to import? You need to import 3 macros. Is this clear, Bhuvneshwari? Yes, sir. Thank you. Next is place the macros of same hierarchy together. So if the macros are of same dimensions and same structure, we need to place them in hierarchical way. Hierarchy means as we stand in assembly line, height wise. As the teacher takes the attendance, roll number wise. So the same way, we will decide the macros to be placed based on their hierarchy. Sir, which one is preferable macro with more fly lines of standard cells with same functionality? I didn't get you, Bhuvaneshwar. Can you please elaborate a little more? So these are the guidelines we are understanding how we need to place the macros. So the first thing is macros placement towards the random logic. If you place the macros in the middle of the core area, if you want to route the standard cells or the two different logics, it is taking longer nets. So this will create a routing congestion. So what we will do? Preferably, we'll place the macros on the corner side or in the edge side. This is the first criteria. Next is based on the flight lines, the communication between macros and macros to IOs, macros to standard cells, connectivity, we are going to align the macros placement. If we place the macros in the two different edges, the communication is very high based on the fly lines, then we'll move the two macros in a hierarchical way, side by side. If the macros to IOP in the communication or the fly lines are more, okay, then what we'll do? We'll move the macros to the edge side. If the macros to standard cells, the communication is more. If standard cells reduces the core area and it has functionality as macro, which one is preferable? Standard cell reduces. Okay, that means you have less number of standard cells. And you have the functionality of macro. Okay. Then what is preferable? So based on the macro definition, okay, if the macro to standard cells communication is more, okay, we will place macro on one corner or one edge side and we'll place the remaining logic for standard cells. Like this. And here I'll place all my standard cells. And I'll make the communication. Make sure that these all fly lines, okay, they are estimated routing lines. The distance, it should be very less. Clear, Bhuvaneshwari? Okay. Thank you. If you are not clear, please put your question more clearly. Okay, this is the third guideline where we have to place macros based on their hierarchy. Next, fourth guideline, there is some notes. Clear, Rambabu. Macro should be placed by taking care of channel optimization to avoid crisscross placement of macros. C. If the macros to macros communication is very high, okay, and if the fly lines are more crisscross, okay, we can change the orientation. Either we can flip the macro or we can change the direction of the macro, like rotate, flip, or any kind of activity we can do on this macro. That is how we need to arrange the macro, like this. So that the connectivity is not more crisscross. Placement should be done in a proper multiple of tracks so that the macros can be routed properly. So if we have more number of macros, all the macros should be placed in a track space, like this. Placement of macros should happen in a way so that the macro pins face towards core to avoid rerouting. So example, this macro is there. This side of pins are communicating to IO and this side of pins are communicating to standard cells. If I place this macro in this direction, okay, my standard cells are sitting here. What I need to do? I need to rotate my macro and make sure that this gets connected. Clear? The sixth guideline. Instead of doing this, we need to rotate the macro and do the routing with less length of nets. Clear? Is everyone able to understand? There is no reply. Tarak Bhuvaneshwari. You are able to understand or not? Yes, sir. Sir, in all macros placed in the chip are in the same size? No, Namini. They can be of different sizes. Is that fine? Namini, come on. The macros can be of different sizes. Next. Hello, keep out margin around the macro to avoid congestion around the macros. Forward. The seventh guideline is if we are having a macro, this is my macro wireless connectivity. Okay. So I am making a margin of this much. This much area of margin I am putting in my core area of my chip. Why? Because to avoid the congestion of routing of nets to the logic with standard cells. This is called hello. It's a hello. That is nothing but to avoid routing congestion and to avoid pin placement congestion and to avoid pin densities. These all are violations. Placement blockages are applied between macro channel. So suppose consider this is also another macro RAM. Okay, I am putting another halo here. Only standard cells can sit here. Do we allow the standard cells to sit in between these two? We should not allow. Why? Because we are making the blockage. We are preserving the blockage to communicate this macro with this macro. So we will not allow this area to be filled with standard cells. We will align the standard cells area in the other directions. That is placement blockages. Avoid stacking of macros. Do not place one macro over the other macro. That will give you the overlap. And that is not allowed also. Try to avoid notches while placement of macros. So some macros, they will have notches. Okay. You have to place this macro in this direction. Then can you change the orientation of the macro to rotate? Can you flip the macro? It is not possible. So do not use such kind of macros. Yeah. There are two questions. Tarak, why we cannot place the same size of macros, sir? So Tarak, it's not our wish. Okay. It's based on the market wish. They design the size of the macros. Some XYZ company designs the macro size of 2 by 2. And the other company designs 1 by 1. What we will do? We want to use both of them. Clear? Does the halo? Yeah, Bhuvaneshwar is asking some question. Does the halo is constant for every macro or it depends on the macro? So halo can be made constant and it can be changed also. Bhuvaneshwar. So if we have the pin density more here towards this macro, okay, we'll place the halo towards this side. We can release this side. If the routing is more towards this side, then we will put a blockage here. We should not allow the standard cells to sit here. That may cause routing congestion. Clear, Bhuvaneshwari? Sir, what does the halo is constant for every macro or it depends on the macro? Tarak, the same explanation as Bhuvaneshwari question. Okay. Next, what is the use of standard cell? So whatever the gate level netlist we get from synthesis that consists of standard cells like NAND gates, flip flops, all these things. Rohit, is this clear? The synthesized netlist will have gates. Those gates are called as standard cells, which are technology mapped and technology optimized standard cells. Clear, Rohit? Okay, sir. Thank you. Everyone is learning subject. Next, the 11th guideline. There should be minimum gap between the macro, as we have told. Okay. See, if you are placing the macros without channel, so how we will route these two macro pins? There should be channel between two macros. And there are some macros without channel also. That's a use case. Okay. We can place, there are no pins this side and there are no pins this side. Then what we can do? We can closely place these two macros to avoid pin density issues. And to place the logic in between those two macros, or the standard cell sitting in between those two macros. Okay. So how we are going to calculate the distance between two macros? That is number of pins, pitch. Pitch is nothing but this one, the gap. Next is into 2. That is double. By available number of metal layers. If the number of metal layers are 5, divided by 5. Suppose, example, I have this side 10 pins. For this macro, 10 pins. And this macro, 6 pins. Okay. And the pitch is 1.2 mm. Okay. So what is the formula? Distance between two macros will be 10 into 2 into 1.2 divided by 5 metals. 5 ones are 5 to 2 is a 4. 4 into 1.2. What will be the answer? That is 4.8 should be the spacing. The distance between two macros should be 4.8 mm. Clear? We should allow channels for routing pins and for buffer insertions, which helps during timing optimization by placing possible required buffers. So if we don't allow spacing between these two macros, okay, and there are communications between these two macros, we should allow some pitch value. If we are not meeting the timing, we should be able to insert a small buffer also, or small inverter, even small gate also. The time this channel should be little more plus or minus 4.8. Clear? Sir, how we can know about metal layers? Boundary people will be giving you. If you want to design 9 metal layer design, 5 metal layer design, 6 metal layer design, 3 metal layer design. Okay. Preferable 9 metal layer is there. 9 metal layer design is good. Why? Because we'll have more number of metal layers. We can get more number of routings. Base layers like oxide, poly, metal 1, metal 2, metal 3, metal 4, metal 5, metal 6, metal 7, metal 8, metal 9. So if we have more number of metal layers, the routing clock nets, we can use different layers of metal nets. So what is the difference between pitch and the distance between macros? Okay. So pitch is nothing but we have macro. These are the pins. All these pins will have standard. This is called pitch. And this is another macro. This has another set of pins. This is another pitch. And this is channel. Clear, Rohit ji? Rohit, okay. Did I made you clear? So the metal layer information will be in the dot left file. Layer extraction form. LEF. Okay. Left file. Next is physical only cells. In physical design, to avoid certain violations like latch-up, iron drop, and to meet chip manufacturing criteria, we use physical only cells. These cells does not have any logical functionality. These type of physical only cells are handicap, boundary cells, well tap cells, decap cells, tie cells, spare cells, pillar cells. So I'll give you the explanation for this. Physical only cells will not have any kind of logic. I have done macro placement. I have done standard cell placement. I have done clock routing. I have done signal routing. Okay, completed. And there is some space left out. What we will do? We will fill with pillar cells. And we'll add some spare cells. And there is some logic. Okay, this logic has to tie high in the or tie low cells. This is one IO pad. This is some tie cell. And I am tying the standard cell to tie low. That is ground. If I want to tie it for high, I'll define somewhere. I'll define it here and I will tie it to tie high cell. This is tie high cell. This is tie low cell. Next is decap cells. Decap cells are nothing but decoupling capacitors. Okay. When we use these decoupling capacitors, there are two nets routing each other. Okay. This is power net. This is signal net. So this has more regression of movement of electrons. This has less movement of regression of electrons. Okay. This will cause crosstalk. So to avoid this, we will insert a decap cell. Next is well-tap cell. Well-tap cell will be inserted in the base layers. That is oxide. Next is end cap cells or boundary cells. These all are called as end cap cells or boundary cells on the core area, die area. Sorry. Pillar cells, sphere cells, tie cells, decap cells, well-tap cells, end cap cells or boundary cells. Clear? This doesn't have any logic. Just to do the metal filling, just to avoid violations, just to avoid latch-up conditions, just to avoid air drop. Okay, we are using these kind of physical memory cells. Clear, everyone? Are you able to understand what are physical memory cells? These are very important for DF, design for manufacturability. If these are not there, okay, they will give you the violations. Air drop means power. Okay, so IR nothing but power. If there is some power drop, okay, these two nets are there. As I am explaining you, these two nets are there. This is power net and this is signal net. Okay, so consider if you are standing on the platform, there is a non-stop train on the platform. What you feel? The air force. The same way, the power net has more amount of electrons flows and the signal net has only triggered amount of electrons flows. So what will impact? They will impact the crosstalk on the signal net. To avoid this, what we are doing? We are inserting decap cell so that this will avoid air drop analysis. Okay, there is some net. This is having power connection. This net is completely driving 5 volts. And the net length is nanometer, 1 nanometer. But we have to route the net with a dimensions. But the dimension is this much only. Then what will happen? This net gets break. That means there is no power. So that is called IR. Clear, Hemant? Hemant, did you understand what is IR drop? Yes, I will. Example, you are using a fan wire, ceiling fan wire. You connect it to your geyser or water heater. Will it survive? Hemant, can you answer this question? Using your fan connection wire connected to geyser or water heater, will that wire withstand or it will burn away? Burn. Why? Because it is not having the capacity to load your geyser. So that is IR drop. This is physical example. Okay. This is on the chip level. Clear, everyone? So far? Any questions? Please let me know. Proceed further. Yes, very well. Thank you. Tarak, you are in sleep? Mr. Tarak, wake up and reply. Yes, sir. Physical cells placement. As we have seen, these are all kinds of physical only cells, like pillar cells, pair cells, tie low, tie high cells, decap cells, well tap cells, end cap cells, where we have to use these cells. Okay. To fill empty gaps in chip placed after completing all sign-off stages and before moving the chip to the fabrication, we have to fill the empty spaces with filler cells. Clear? Next. Spare cells. To perform engineering change order in design, placed during placement stage and in few cases placed during the routing stage. Okay. Spare cells. We place the spare cells at the time of placement or ECO, engineering change order. To, yeah, Bhuvaneshwari, why need to fill with cells? Why it cannot be left empty? So there is metal density rules. Okay. So you build a sump in your house. You are not closing that sump with a lid. What will happen? Okay. You need to close it with some lid. There may happen someone fall into that sump. The same way, as per the metal density rules of fabrication, we need to fill the empty spaces with similar metal layers, whatever is used. Clear, Bhuvaneshwari? Okay, sir. Spare cells. So spare cells are done at engineering change order. Engineering change order is nothing but after completing the full design. Okay, if you want to change some logic in future, some part, okay, then we will insert some spare cells. Or else, at the time of placement, we place the spare cells. In few cases, at the routing stage. These spare cells does not have any functionality, but they are the cells which are going to take the load or some other kind of activity to save other parts of the design. Next is tie cells. As I have told you, some standard cells we want to tie it to high and some net we want to tie it to low. These cells are placed at placement stage. Next is decap cells. To avoid IR drop, we will use decap cells. If the decap cells are there, if there is any IR drop, short or open, okay, the voltage will be flooded to ground terminal. Next is well tap cells. To avoid latch up condition, placed during floor plan stage. So latch up condition will apply at the base metal layers. Okay. To avoid latch up condition, we will be using well tap cells. Next is end cap or boundary cells. To show end of side rows and to avoid damage of the cells during the manufacturing of chip, we will place this end cap or boundary cells at the floor plan stage. Similarly, okay, I will give you a practical example. So when you are putting mehndi, okay, on your hand, it will come like a strip, small amount of strip. Similarly, when the fabrication tool will lay the layout of the design, it will do the same way. Okay. To avoid damage of cells, we will use end cap cells. By mistake, the tool is getting connected to the end cap cell. There is no logic. So we will not get any effect of damage of the logic or macro or cells inside our core area or design. So spare cells. So spare cells are like some of the basic gates. Okay. So we can use just for timing analysis. If you want to increase the delay, if you want to decrease the delay, and if you want to check the logic, whether they are working or not. If the voltage drop is more, we want to derive it to some cell. At that time, we will use these spaces. We will not change the complete logic, but we will try to meet the logic in engineering change order. Bhuvaneshwari and Tarak, engineering change order is nothing but if we are unable to meet the timing, area, and power of our logic design, okay, in the complete stage of routing, okay, in the stage of ECO. ECO is done after routing the chip. Complete placement, CTS, routing, everything is done. But still we are not able to meet the design logic. Okay, in the synthesis time. Then we will try to insert some spare cells. That is what ECO cells are inserted at the routing stage also. Clear so far? It doesn't have any logic, but we'll use them to avoid some safety for our design. Why we use our helmet on a bike ride or a wear seat belt in a car ride? Just to avoid safety. Same way, we will use spare cells. All these physical only cells are safety cells for our chip. Next, power planning. So we have completed floor planning. In floor planning, the next concept is power planning. Okay, the power planning is nothing but we have to route power nets. To route power nets, usually what we will do? We have Srisailam or Nagarjuna Sagar or Vijayawada or NTPC thermal power stations. There is a power grid. That power grid will distribute to the districts. And from the districts, substations, we will get to the colony transformers. And from colony transformers to the individual house meters. This is how the power distribution is happening in our real life. That is electrical lines, high tension lines. Similar way, okay, we have a power ring. We have a power ring. The blue color is power ring. The power rings are connected to VDD and VSS. VSS is nothing but ground. Okay. The next, to give the power to the inside logic, we are drawing the power strips. VDD power strip, VSS power strip. VDD power strip, VSS power strip. This blue color is generation of power, or we are getting from the external source to the chip. And red color lines are giving it to the core area. And from core area, we are getting it to the standard cells or macros. This is how we are going to distribute the power completely on the chip. power ring, power straps, power pins. Okay. So here you can see the blue color lines in between core area and die area. We have power ring. And next is the connectivity between IO ring and power ring is called power trunks. And inside the core area to the IO ring, we are drawing power straps. And here, whatever the follow lines are there, this gets connected to the power internally, the core area. And already macros power pins are connected. Clear? This is how we are going to do power plant. So how many stripes, how many rings, how many trunks, that depends upon the mathematical calculation. Per day, thermal power station generates 100 kVA of power. But each substation can take only 11 or 33 kVA or 22 kVA. And each colony or town can take 5 kVA or 2 kVA. Based on that, we will get 230 to 240 volts per house. Clear? Bhuvaneshwari, Tarak, Siddheshwar, and all the participants. Hope you are listening and understanding the concept of VLSI physical design. Jai Shri Ram, Ishwar Sai Royal, my Royal Enfield. Clear? Done. See, this is how we will do the top level power planning. We will have the power ring. Based on the power area, we will draw the power stripes. User can specify number of straps, minimum number of straps or maximum number of straps, and width of the each strap, minimum width or maximum width. Okay, and width of the ring based on the power consumption. So the ring should be high tension line. Okay, and the power straps should be transformer lines. Okay, and the connectivity to the standard cell should be like our house. Clear? So it depends upon the logic consumption power. If the macro needs 3.3 volts, the width and the dimensions of the power for each and every net should be calculated. Clear? And if you are using a macro block level power planning, okay, this is how the block level is done. For each and every block, they will be having the power ring, and for the power ring, we will get VDD and VSS, and internally this macro has power routing. And if it is a macro, directly it can be connected based on the pins available. Then it can be directly drawn like this, power routing, based on the stripes. Clear? Power planning. Steps in power grid planning. Decide the number of power pads. So I have core area, die area. Okay, I have this IO pads. Based on my power consumption in the core area, I need to decide how many number of power pads should be aligned on the IO ring. Decide which metal layers will be used for power routing. Usually higher metal layers. If I am considering metal 9 and metal 8. These two metal layers, I will be using it for VCC and this is for ground. Okay, define width of the top level power bus. That is power ring. Determine the structure of the block and macro level power planning. If I am having a macro, I need to design a ring for this. I need to design a straps for this. I need to connect VDD VSS. Clear? Next is power net analysis. Power net analysis means calculating the how much power each and every cell or logic is consuming and how much area power we need to distribute. Next is after power planning, what all checks we need to do? Check power ground nets DRC. DRC means design rule check. As I have told you, this is power net and this is signal net. There should be minimum distance between these. Else we need to install a decap cell. Else there becomes a crosstalk. This signal will not work. Only power will work. And if there is higher drop analysis, those all comes under the DRC. And PG connectivity. Connectivity means the net is very thin. Okay. The driving capacity of the net for the power is very less. Then this net gets break. And I am routing a power net to this logic. Okay. And this is metal 7. And I have metal 8 ground. So I need to put a wire here. If I am missing wire, I will not get the connectivity. Okay, these all are the commands. Tarak. These commands, if you enter in the EDA tool, Cadence or IC compiler, okay, in Synopsys, they will give you the information. EDA tools will give you the information there. Okay, clear? So we'll directly jump to the demo. Give me 2 minutes. Is everyone able to see my screen? Yes, 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 yes. So this is Cadence tools. You know us. I'll exit the tool. I'll start how to launch it. Is it? Okay. After sourcing this, I'm running the tool. So my tool version is 20.1 and it is taking 8 CPUs and the CPU is of 2.6 gigahertz. Okay, this is the version and this is checking the licenses and it will launch. So this is the physical design tool. Is everyone able to see? I'll just explain today the options. These are import design. Okay, as we have discussed ECO. Okay, this is about ECO. And next is floor plan, specify floor plan. Next is power plan. Next, what we are going to do in the power planning. Next is placement. Okay, next is clock tree. Next is routing. Next is timing analysis. And verify is design rule verification and layout verification. And we have engineering change order, ECO, where we do the timing, power, and area analysis based on our optimization. And we have here the metal information in the right side. See, they can be up to metal 31. This tool can support up to metal 31. But my PDK or my standard cell library has metal information. By clicking these options, I can get blocks, standard cells, towers, scale only cells, and all this. Okay. And IO ring, area of the IO ring, and all this. Next is module. If I have selected a module, I am partitioning that module, then I have to check this. Next, cells, blockage cells, pin shapes, and cell layout. If you have any blockage, which metal we are using for blockage. Next is rows, standard rows. As we have seen, there are some standard rows. These lines, horizontal lines. Those are called standard rows. Those standard rows are defined in which pattern. Next is floor plan. Based on the floor plan, which metal layers it has to use, which color schema it has to use. If there is an overlap in the block, if there is an overlap in the IO, if there is an overlap in the macro, it will hide it using that colors. Okay, we need to understand the color first. Next is partition. Partition is nothing but if you want to separate two blocks of the design, then we call it as partition. Next is power net grounds. So this nets, this color or this kind of pattern in the nets will define power. Next is overlay, pin density, metal density, time mapping, power density, congestion. Overlay. Track. Nets, signal nets, power nets, ground nets, clock nets, and special nets. Special nets are like presetter, and all those things. Route. Shielding between the nets, pitch wire, trim metal. Trim metal is nothing but how to cut that metal. Next, wire definition, metal field definition, fairly global net, shielding the net. Shielding the net means if the net has collision, then we have to shield that net. And this is about layer information. And this is about bump information. Bump is nothing but I have a macro. Okay, I can drop two bumps here. Bumps are nothing but two power channels, and I can route VDD and I can route ground. So using these pumps, I need to supply the power to my macro. That is pumps. Clear? Sir, this practical programming, do in microwind also? Rajeshwari, not sure, Rajeshwari. I have heard about this microwind tool, but I'm not sure whether it is possible or not completely. Okay, but we can try little, not much, complete chip. Okay. To learn the complete chip design about physical design, this is possible. Next is grider. Miscellaneous, which colors we need to use? Violations, basically. Aggressor net or receiver net, port numbers, all this we can choose in this miscellaneous. So coming to the design, okay, import design. So I am designing. I have my Verilog synthesized netlist. I am going to import that. For that, I need to go for import design. Innovas. This is my synthesized netlist. This added close. And the top level module name is serial. That. This is the top level module name of my Verilog netlist. Okay. Next is physical libraries. What are the physical libraries I have? I need to add to it. This is the physical library. Okay. I'm adding to it. Next, I'm defining governance. VDD, BSS. Next, multi-mode, multi-core name. That is nothing but if I have any constraints file or if I have any case analysis. For that, my tool will generate multi-mode, multi-corner simulation file. This file has to be loaded at the time of synthesis. Then click OK. So this will run commands in the background. So I'll get some core area and die area based on my standard cells A, C. Here I got my area of the chip. So if you zoom in, here, you have standard cells. See, these all are your standard cells. These are the pin connectivities. Okay. So these horizontal lines are called follow lines. What we have seen in the previous slide. Okay, these lines. In these lines only the standard cells gets placed. That is the tile height and width. The height of the standard cells all are same height, but the width may vary. That is a thumbnail rule. Here so far everyone? Any question? So in the next class, we'll proceed with the practical part, how to design the complete floor plan placement and power plan. Okay. So for today, we'll wind up the session. Any questions? I'll wait for 2 minutes. And stop sharing the screen. If you have any questions, please let me know. Bhuvaneshwari. So the top level power planning will differ from the block level power planning because the block requires 3.3 volts. But the top level power planning requires the whole consumption of power of the chip. Okay. So my block requires only 3.3 volts. Based on that, I'll draw ring or I'll drop a bump. I'll draw the metal rails, power rails, VDD and VSS. Okay, only for the block, 3.3 volts. And if it is for the full chip level, I need to know each and every block, combine it together, how much power area it is consuming. Clear, Bhuvaneshwari?